everybody, this is Mr. Folly, and welcome to the key for Big Idea 7. Wow, my name didn't look very good there. As a reaction means only reactants. As a reaction proceeds towards equilibrium, the rate of the forward reaction will decrease. So remember, if you're looking at the rate of these things, the amounts would go down. Well, no, it wouldn't. I drew that wrong. It would. So the slope starts out near infinity and it ends up near zero, so the rate decreases. The rate of the reverse reaction would increase. So if I'm looking at the reverse reaction, which would be a product starting at zero, it would increase for a while and then decrease because it starts out with no slope. Okay, the reverse reaction increases until equilibrium reaches because it starts at zero and reaches your equilibrium speed. The concentration of the reactants will increase. Oops, no, it won't. Concentration of the reactants will decrease. My dog came to say hi. The concentration of the products will increase. Okay. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse. The rate of the reverse reaction is equal to the rate of the forward reaction. The concentration pressure of the reactants, this is at equilibrium. At equilibrium, the concentration or the pressure would remain the same. Remember, that would be a plateau. The concentration pressure of the products would remain the same. And let's move on. The reaction shown below is conducted and data is collected. How does the rate of the forward reaction compare to the rate of the reverse reaction from 0 to 5 minutes? So from 0 to 5, what the rate is it's change in x over change in time. So let me throw that in my calculator real quick. So I'm going to do 4.1, and these would be absolute values. E negative 2 minus 5, E negative 2, whoops, I put 52. So x is 0.009, negative 0.009, and y is 9e negative 3. So if I have 9e negative 3, 1, 2, 3, 0.009. Ooh, that's really crazy. That is, yeah. So how does the rate of the forward reaction compare to the rate of the reaction from 0 to 5 minutes? Same. And you saw my change in there. Change in x, y over change in t. At what point does the system reach equilibrium? See, that's what point does it reach equilibrium? It should be right there. So, but it doesn't. So, are these? So that's really weird that it's the same right there. Yeah. At what point does the system reach equilibrium? You would think that those rates would be the same. I just want to check that math again because that doesn't seem right. So it's 0.9 e negative 2 divided by 5. And that's 1.8 e negative 6. Oh, I forgot divided by 5. And then 9 e negative, oops, I put 9 e negative 5. So 0.9 e negative 2, that's subtracting these two, divided by 5, equals 0.0018. And then 0.009 divided by 5. Okay, there's the rates are the same, but the concentrations are changing. So where do the concentrations start to be the same? Is at 155 minutes. 155 minutes because molarities are constant and rates are constant. So that's really weird that that rate was the same in the beginning, but that's, there, because it's negative and positive, those aren't the same. I'm so sorry. At equilibrium, what physical changes can be observed? None. It looks constant, but changes on a molecular level. Okay, the reaction above occurs in an evacuated 373-degree container. Concentration of each species is measured over time that are used to make the graph shown above. When does the system reach equilibrium? It reaches equilibrium at 70 seconds because molarities are constant. I could also say the change in concentrations over time are equal. So change in molarity over T are equal. What is the value for K? So remember, K is products over reactants. Do we have coefficients? We do. So I'm going to have N2O4, which is going to be 4. Okay, so make this bigger. NO2 squared over N2O4. So NO2 at equilibrium is 4E negative 2. Whoops. So it's going to be 4E negative 2 squared over, and then let's see what N2O4 is. N2O4 is going to be 12E negative 2. And that is not squared. Let me just make sure that's right. So I think I might have them flipped, because usually you end up with more products than reactants. And that is true. NO2 is 12 squared, N2O4 is 4 squared. So 12E negative 2 squared over 4E negative 2. 12E negative 2 squared over 4E negative 2 equals 12E negative 2 squared divided by 4E negative 2.36. In that case, should be capitalized. At 60 seconds, the rate of the forward reaction greater than, less than, or equal to the rate of the reverse reaction. Explain your reasoning. Okay, so remember, we're going to look at the slope of the line. So at 60 seconds, oh man, I guess that's where it's, if I were to draw that tangent line right now. So the forward reaction would be N2O4. I would say, or is that where it goes flat right there? I guess that's where, depends on where you think this is. So I guess that's the point where it first becomes flat. So when I said it was 70, I suppose it first becomes flat at 60. I'm going to change that one. So at 60 seconds, rate of forward reaction, it's equal. Both slopes equal 0. Therefore, rates equal 0 and are equal. Why is NO2 greater than the slope of N2O4? So on each of these, NO2 is a coefficient of 2. Oops. Put my drawing in here. I figure out how to do that. Get rid of that. NO2 has a coefficient of 2, which is double N2O4 and makes NO2 2 times the slope. Okay, so remember, you're going to have those coefficients that are going to mess you up a little bit. Okay. Two different compounds of the same temperature have the same volume of a volatile organic compound. Two different containers, same temperature, same volume, the liquid organic compound is in equilibrium with the vapor phase. Explain why, regardless of the size or surface area, the equilibrium vapor pressure of both containers is the same. What you're going to have is K is a constant, which is going to be the pressure of the gas, and that's it, right? So if I had a reactant and a product, the other one, if I thought of it as a liquid, remember, pressure of a liquid is constant. So that means this won't be there. And what happens to it is this gets incorporated into K. So what you can say is Kp is the pressure of the gas. So algebraically, the volume doesn't affect P. P being pressure. Use the graph below to answer the question to follow about that reaction. We've got coefficients, should have different size slopes, etc., etc., etc. What is significant about T1? I guess we're saying T1 is where equilibrium occurs. What is the value for Kc? So Kc is going to be, I'm going to do it up here. K is products, raise their coefficients, over reactants, raise their coefficients. And then we get these from here. Ooh, what is the value for Kc? You need to know these numbers. So I have to give you these numbers. I admit I added this and didn't really look at what it was. So I'm going to make up some numbers for this. Let's say this is, no, I don't want to do it because then I'll get all kinds of icky with the stuff. So if I call this A, well, let's make it as cheesy as we can. So this is be the molarity of H2. I'm going to put H2 in brackets. And H3 in brackets, meaning molarity, and N2. So this would be it. Why does H2 decrease faster than NH3? Well, again, so H2, notice that slope is more. H2 has a larger coefficient. What is the rate of disappearance of H2 compared to the rate of disappearance of N2? It is 3 to 1 because of the ratio of coefficients. How does the rate of appearance of H2 compare to NH3? It is 1/2. I'm just showing one as a ratio and one as a fraction. 1/2 because H2's coefficient is 1. Is that right? Make sure I got it right. Oh, man. Okay, what H2 compared to N2? H2 compared to N2. Well, that's 3 to 1. And then H2 compared to NH3. Well, it's 3/2. That's what we get for not looking. 3/2 because H2's coefficient is 3 and NH3 is 2. What point is the rate of the forward reaction equal to the rate of the reverse reaction? T1. And that's typically when the changes are 0. All right. At what time is equilibrium established? So that means I need to have the same concentration of stuffs all the way through. So let me do this, this, and this. I'm going to try and skip the first one, save myself some time. So I've got 1, 2, 3. 3 of those. Got 1, 2, 3, 4, 5. Got 5 of these. I've got 1, 2, 2. So we got 5, 3, 2. Here we go again. Big circle, dot, big circle, dot. Big circle, 1, 2, 3, 4. Okay, so I know that's not equilibrium. little dots, I've got 1, 2. And then ring dots, I've got 1, 2, 3. So here we go. Big rings, little dots, big ring, little dots. Remember, little baby Chucky, count and compare. 1, 2, 3, 4. Okay, that's the same. 1, 2. That's the same. 1, 2, 3. That's the same. So, oh, look, it really likes that screen. So what time is equilibrium established? 200 seconds, because molarities are constant at 200 and after. Okay. All right. So would the value of K be greater than 1, less than 1, or equal to 1? Explain. So somewhere I've got my reaction. So I've got this. I've got XY. So XY is 3, and the other ones are 4 and 2, right? K would be less than 1 because there are more products than reactants. I could also call each one of those particles a mole. Come on. Each one of those particles a mole and actually calculate it. So I could write the K expression of this xy over x squared y squared, and then so that would be 3 over, I said squared, sorry, 3 over 4 times 2, which is 8. What does the value of K indicate? The amounts of reactants and products. Bigger K means more products. Now it says and reactants, so I'm going to put in fewer reactants. Use the figures below to answer the questions that follow. Figures, I was hoping that would just go back to what it should have been. Reactants. All right. Has the system reached equilibrium? Time 1 and time 2. You know what I'm doing again. So I got double ring. I got ring dot. I got dot. So double ring. 1, 2, 3. Second one. 1, 2, 3, 4. Okay, so those are different numbers. So that means it's not at equilibrium. System reached equilibrium? No. Molarities are not constant. What can be inferred about the relative rates of forward and reverse reactions between time 1 and time 2? Okay, so that means I'm making y2. So y2 went up. So if y2 went up, that means xy should go down. Let's just confirm that. 1, 2, 3, 4, 5, 6. So that was 6. 1, 2, 3, 4. That's 4. Okay, so what can be inferred about the relative rates of reverse reaction between time 1 and time 2? Forward is greater, positive, because, wait. What's happening here? Nope. I'm making reactants, so the reverse is greater because reactants are forming, right? So x2 was that, or y2 was forming, yeah. Student makes the claim shown in the box. Do you agree or disagree with the statement? Explain your reasoning. The equilibrium of the forward and reverse reaction stop occurring because the concentration of reactants and products will change. Do I agree with that statement? No. At equilibrium, the molarities are constant, but both forward and reverse reactions occur at the same rate. Okay. Of the two graphs above, which shows the concentration reaction change over time to reach which shows how the concentration of a reaction changes over time to reach equilibrium? That would be B, because lines are zero slope, but not equal, which shows how the rates of reaction change over time to reach equilibrium, just by your answer. A, because rate are equal if lines are equal value, where I drew the line. On both graphs, draw a vertical line to show where equilibrium is established. Oh, there you go. Use reaction below. Uh-oh. Let that stay there. Use reaction below to answer the questions that follow. Write the expression for the equilibrium constant Kc for the reaction. Okay, here we go. K equals Z cubed over X squared Y. Determine the value of Kc if the molar concentrations are this. So K equals 4 cubed over X squared. I'm going to make that 4 right away, times Y, which is 0.5. Let's see here. 4 cubed divided by 4 times, 4 cubed, move it out of the exponent, divided by 4 divided by 0.5 is 32. Determine the partial pressure of each gas. The total pressure is 17. The gas are in a 17-liter container. Oof. Okay. So I think I got an ice diagram this bad boy. Total pressure is 17. Oh, no. So what this means is X plus Y plus Z equals 17. So those would be their pressure. So, and then I would have partial pressure of each gas. Okay, so using this part up here, we can say that because they're all gases, that those would be the same. So the total pressure was 17 then. What we could do is use that ratio, I suppose. Okay, so at equilibrium, I would have let's see here. You know what? I'm going to skip this one because there's a handful of things I think I need a given amount on this. So we're going to check and see if I can get that given amount. Because on the end, we've done this before where we've got the equilibrium value. So if these are the equilibrium values, and I guess we could do that, 2 molar. So I guess we know the ratios here. If we have these ratios, we'll do this. If we have this ratio here, we have X plus 2X plus Y yields 3Z. 2X plus Y is in equilibrium with 3Z. And if we know this is 2, and this is 0.5, and this is 4, we know these would be our ratios. I guess so we could do the pressures for each one of those because those concentrations would be mole factors. And those would be total pressure of 17. So if I do that, 2 plus 0.5 plus 4, I guess that's 6.5 P. So 6.5 P equals 17. So then P is going to be 17 divided by 6.5, which is going to be 2.62 atmospheres. And then we would use those multipliers right here. So I'm going to change this to a different color. Hopefully it's not super thick when I do it. Oh, but it is. So 2.62. So 2 times 2.62 is 5.2. That's still thicker than I want it to be. And then 0.5 times 2.61538 is 1.31. And then 4 times 2.61538 is 10.4. Okay. So if I do that, then those would add up to be 17. That'll work. And then determine the value of KP. KP is my products, which would be 10.4. Whoops, I made 100 before. 10.4 cubed over 5.3 squared and 1.3. That's hard. That's a mean one. 10.4 cubed divided by 5.3 squared divided by 1.3. That'd be 30.8. And that's it. So that'd be atmospheres. I guess you don't put a units on Ks, because that would really be, I guess it would be unitless anyway, because all the Ks would cancel. All right. Solid carbon dioxide were placed. Solid carbon and carbon dioxide were placed in a 2-liter rigid container, and the reaction represented above occurred. As the reaction proceeded, the total pressure of the container was monitored. When equilibrium was reached, there was still some carbon remaining in the mixture. Results are recorded in the table below. So notice that I have one gas here. I have two gases here. So if pressure is going up, it's going to the product side. Pressure is going up, it's going to the product side. Okay. Write the equilibrium expression for Kp for the reaction. So I'm going to do that over here. Okay, so Kp is going to be the pressure, CO2 squared, over the pressure, again, it's products over reactants, over CO2, except for, I thought I misread it, pressure of CO over the pressure of CO2. Calculate the number of moles initially placed in the container. Assume the volume of the solid carbon is negligible. Okay, so number of moles of CO2 would be PV equals nRT. My pressure is 5. My volume was 2, I believe. Yep. N 0.08206. The R values given on the equation sheet. And 1160. Hotsy totsy. So 10 divided by 0.08206 divided by 1160 equals N equals 0.105 moles. Now, what time does the system reach equilibrium? 8 hours. Pressure is constant. And my eraser is not my friend today. For the reaction, mixture at equilibrium at 1160, the partial pressure of CO2 is 1.63. Partial pressure of CO2. Okay, so for the reaction mixture at equilibrium at 1160, the partial pressure of CO2 is 1.63. Calculate the partial pressure of CO. Okay, so what I know already is I can figure out K from above. So that means it's going to be the total pressure of the gases. Okay, so I'm going to start with partial pressure CO2. So I guess I got to really figure out equilibrium constant. Partial pressure CO2. So I'm going to have CO, as far as I care, is in CO2. Make sure I got this right. The CO2 is in equilibrium with 2CO. And I know I'm going to start with the partial pressure of CO2 was 5 and 0. The pressure of CO2 at equilibrium is 1.63 minus x plus 2x, 1.63. So I can figure out what x is. So 5 minus 1.63 is 3.37. So that means that that's 3.37. So this is going to be double that, 6.74. The partial pressure of CO. The partial pressure of CO would be 6.74 atmospheres. Make sure I have that right. I'm still afraid it's CO and CO2. It's CO2 on the left and 2CO on the right. Okay, good. Divided the equilibrium constant Kp. Kp, we wrote it down before, as products, 6.74 squared because your coefficients over reactants, 1.63. All right, 6.74 squared divided by 1.63, 27.9. And there's Kp. According to the K value calculated in D, is the forward or reverse reaction favored? Forward, K is greater than 1. Same number of moles of HCl and O2 are used in the reaction below. Okay, same number of moles for each one. Answer the question the following about the reaction after it has reached equilibrium. So I'm just going to say 1 and 1. How would the molarity of H2O compare to the molarity of Cl2? Explain why, referring to the reaction stoichiometry. It would be equal because identical coefficients as products. So I'm pointing out their products because reactants and products would be starting amounts weight affected. How would the molarity of HCl compare to the molarity of O2? HCl is less because a larger coefficient loses more. Yeah, there you go. Use the reaction above to answer the questions about, I guess I gotta leave my more in my period there. Use the reaction above to answer the questions that follow about Q, Kc, and the direction of the reaction. All right. 0.1 mole sample of each of the 4 species in the reaction, as represented above, is injected in a rigid 1 liter container. What is the value of Q? 0.1 mole sample of each in a 1 liter container. So I'm going to write Q equals, even though it's the same as K. Everything's a gas, so it's included. CS Lewis 2 squared times hydrogen to the 4th over H2S squared and CH4 to the 1st equals, everything was 0.1, right? 0.1 and 1, 0.1. I'm going to rewrite that so it's more legible. I'm going to try and rewrite that so it's more legible. 0.1 times 0.1 to the 4th over 0.1 squared is 0.1. Boom, boom, and I get 0.1 squared as my final answer, which is 0.01. Okay, which direction will the reaction proceed to reach equilibrium? So I like to put them into similar things. 0.01, this is Q, and then K is going to be 0.12334. Q is bigger than K, so it has too many products. So shift to the left-hand side because right now there's too many products. Remember how Q and K are products over equilibrium, products over reactants. So if Q is too big, you get too many products, start turning your products into reactants. Which species will have the highest concentration at equilibrium? So I'm shifting to the left-hand side. It would be H2S because it will make 2 times more than CH4, and the left-hand side increases. So the right-hand side is going to decrease, so that's it. All right. Determine the direction the reaction will proceed to establish equilibrium given the initial concentrations of each experiment. Okay, so the value of Q. So I'm going to write my Q expression right here. Q equals Y, well, X, Y over XY squared. Okay, so this is going to be 0. Direction will proceed to equilibrium. So I'm just going to say that if Q is bigger than K, it'll shift to the left-hand side. Q is less than K, it'll shift to the right-hand side. So value of Q is 0, so Q is less than K. Direction will proceed right-hand side. Will more reactants or products form in order to reach equilibrium? Will more products or reactants form? So this means right-hand side is going to be products. The rate of the forward reaction is greater than. There you go. So now let's plug these in. So I've got X times Y. So 0.2 times 2 divided by 0.01 squared, 4,000. So Q is bigger than K. It'll shift to the left-hand side. Will more reactants or products form? Reactants. So the reverse is faster. Oops, sorry. The rate of the forward reaction will be less than. So this one, I've got 0. Oh no! Oh no! Value of Q is undefined. All right. I'm going to think of it as 0 though. Will the reaction, which way will it proceed? Well, it's going to start making reactants, so it's going to shift to the left-hand side. Because it's less than 230. Yep. Oh, wait a minute. I don't know, I'm not going to think of it as 0. I guess if it's undefined, that's why undefined is undefined. On this one, if I don't have, remember how you can't have a time when you don't have any, it's going to shift to the left-hand side. So what's favored is the reactants. So the forward reaction would be less than, it would be 0 for the other one. Okay, so here we go. X times Y, 0.05 times 0.05, enter, divided by 12. 2.08 e negative 4, 2.08 e negative 4. That's less, Q is less than K, so it's going to shift to the right-hand side. Shifting to the right-hand side, products are favored. And if products are favored, the rate of the forward is greater than. I'm going to let my greater than settle. So here we go. Oops, I need my equation again. X times Y over XY. So 1, that's going to be 1. Remember, K was 230. So Q, right? So K is 230. So Q is less than K. So it's going to shift to the right-hand side, which would be the products, which means it's greater than. Let's see here. Short-term memory getting me again. XY over XY squared. So 0.97 times 0.97 equals, divided by 0.064 squared equals 230. 230. What is favored? None. None. And equal to. For any situation where Q is greater than K, explain the reasoning for the direction the reaction will proceed. So if K is greater than Q, that means, remember how K is products over, well, I'll do Q. Q is products over reactants. And if K is too big, that means Q has too many reactants. So the rate of forward is faster because there'll be more collisions. If Q is less than K, explain your reason. Q has too many products, so rate of the reverse is faster because there'll be more collisions. When Q at equilibrium, rates are equal. I have no idea what you're saying. Just talk to me. And that's it. So I will say toodles. Toodles.